All right, we're back.
Well, it's been a while, Zach, since we recorded, since we put out an episode, all the things. And just excited to connect again and chat about the most recent Nobel Prize in Physics 2022.
Yeah, me too. It's very related to stuff we've talked about. So it seems like we should touch on it.
Yeah, for sure. Do you want to give a rundown of what the prize was awarded for?
Sure, yeah. So generically speaking, or like in a very broad strokes, it's kind of for this like class of physics that I don't know they've given a Nobel Prize in before, called like quantum foundations, which is, like we've talked about before on the podcast, we really don't have a good understanding of like kind of what's happening underneath the scenes in quantum mechanics. And maybe that's okay. And maybe some people want to know more, but people that kind of study this thing and ask these sorts of questions like Bell did, that has become like kind of its own field called quantum foundations, trying to understand some of this stuff more deeply than we do already. And so specifically, this is basically like, I guess they normally give the Nobel Prize to experimentalists. So I don't know if John Bell, if he were alive, would have fully gotten it. But basically, this is all on the work of John Bell, like that he started, and which we have talked about before on the podcast. And the basic idea is this is all about entanglement. This whole award. Basically, the first two people proved Bell's theorem, which is related to entanglement. And I guess we talked about Anton Zeilinger, but I don't know I can't remember exactly what he's done with quantum entanglement, but I think it was beyond just proving Bell's theorem. I think he's done a lot more than that, like actually used it for useful things like quantum computers and I think he invented quantum teleportation, maybe, if that's
like the experiment to actually do it.
Yeah, exactly.
Yeah. So the language of the award was for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So that's the like official award language. And yeah, we talked about Bell's theorem. If you go to thehyperfine.com, 21st of March, 2019, we have a Bell's theorem episode. So Bell's theorem and EPR we talked about. Went into detail about what Bell's theorem is, what are the inequalities, and what it means to violate them. Basically, Bell set up an inequality that said if this inequality is true, if experiment A is less than the result you would expect from theory B, then quantum mechanics is wrong. And then all the experiments are coming out saying the inequality doesn't hold, so quantum mechanics seems to be correct.
Right.
Which is what this award was for the people doing those experiments.
Yeah. So that's like the thing that I kind of learned was that Bell came up with the idea, like we talked about, but I guess, he didn't really test it.
He was a theorist at CERN.
Yeah, or at SLAC, I think.
Oh, SLAC? Sorry.
Yeah, I think he was a Bay Area person, which is nice because another Bay Area person got the award for it. Clouser was a Bay Area guy. They basically took his idea and created like a testable version of it, is what Clouser did. He was one of the first people to do this test. He created his own inequality, which is a type of Bell inequality, and its short name is the CHSH inequality. His name is in there. I don't know what the other letters stand for off the top of my head. Oh, here we go. It's Clouser, Michael Horn, Abner Shimony, and Richard Holt. So the four of them created the CHSH inequality, which allowed them to test Bell's theorem by creating entangled photons and measuring their polarization along two different axes by two different people, Alice and Bob, as is canon. And those experiments, basically did exactly what Bell said. If you can't get a value bigger than this, then quantum mechanics is wrong. And if you get a value bigger than this, well, then quantum mechanics is correct. And I guess, like kind of this, I think that's it. That's all I would say.
Cool. And so when I messaged you a couple days ago saying, hey, we should record about this, you were saying you're taking a class that it directly relates to. Is that?
Yeah. So, we don't have to go deep into personal lives, but part of the reason we haven't recorded in so long is we're both busy people, but I have applied to grad school and got into grad school at San Jose State.
Congrats.
Thank you. I've picked up my life and moved it, and am trying to figure all that out. So I'm getting a master's in physics right now, and so I'm taking a quantum computing class, and we're literally talking about like entangled states. And I guess one of the first things I should say is I haven't listened to the previous Bell's theorem recording, but you sent me a quote that I said on it, which was mostly like, it was along in the spirit of true, but it was wrong technically. In that, I believe I said something about like either it's superposition or there's like a DNA part of the particle. And I think Bell's theorem is more about entanglement than superposition. Like entanglement is the magic thing that is not real magic, but it's the special thing that gives that allows quantum mechanics to be quantum mechanics. So I'm taking a class right now where we're kind of talking about quantum computers, which basically are these devices you've probably heard about, but in that you create a thing called a qubit, which a single qubit can be in a superposition of states. But if you take two qubits and you put them together, the pair of qubits can be in something called a superposition as well. But you can create a state between two qubits that can't be represented as a superposition of two other states. And that type of state is called an entangled state. And that's what Bell was thinking about. That's what Bell created through not fancy quantum computers, but just through the conservation of angular momentum in his the way he was talking about through energy and momentum. But we now can like create them at will with quantum computers. And that's kind of the thing that's the driving factor for what makes quantum computing. Quantum computing is our ability to create these states that you can't express as like a superposition of two other states, which like the technical term is it's a tensor product of two states. If you can express your two qubit system as a tensor product of two states, then it's not entangled. But if you can't express it, if there's no way to multiply these two states together to get the state that you're in, then it's called entangled.
Got it. And then, so they won the last part of their prize announcement was for pioneering quantum information science. So that's all this stuff with quantum computing. The entangled states lead to the ability to do computations and encryption type things.
Yeah. I'm just getting into this in my class, so I don't know too much of the details, but there's a lot of things you can do with a quantum computer. Like there's this thing called the no cloning theorem, which basically means like I can, Alice and Bob can set up some, they're trying to create a key in which they can communicate securely over. And we've also have an episode on encryption that you can listen to. I don't remember which episode number it is, but
it's not quantum encryption, just like SHA,
just regular encryption. But it has the same idea in that like the basic part of encryption is you have to exchange like a key, and you want to be able to then be able to communicate, and the only people with the keys can decrypt what is happening. And like how you exchange the key is kind of like the hard part to figure out. And in quantum, the no cloning theorem basically means that there isn't a way to directly copy one state. Like there isn't some operation that you can do to copy an entangled state into another entangled state. You can do some states, but there's no general operator that does it for every state. And so the idea behind this encryption thing is like Alice and Bob, they spin up a bunch of states, and they send states back and forth, or they send, like, Alice makes some states, she sends them to Bob, and they measure the states. And I'm going to give very broad strokes here, but they measure the states, and there could be someone in the middle. You can call her Eve because she's eavesdropping, and Eve may or may not be like measuring the qubits as they're being sent back and forth between Alice and Bob. And if she is measuring the qubits, she can measure it, but that collapses the state, and she can't copy it. Like, she can't copy and measure it. She can do, I guess she can't ever copy it, but it's like once she tries to measure what the state is, she has now fundamentally altered the system.
Mm-hmm. Any interaction.
Any interaction that she does, the eavesdropper, is going to mess up, is going to be detectable by Alice and Bob. So basically what they can do is there's an algorithm that says, like, they can exchange bits in a particular way, or qubits, and they can measure them. And if there's a statistical difference in their measurements, they know that someone in the middle was listening. And so they can say, okay, we're not going to use this key because someone was listening. But if they get the same results in their measurements statistically, then they know, okay, no one listened to this. And so we can use some of this data as a key, and then now use that to communicate. So it doesn't like prevent someone from listening, but it lets you know if someone was listening on the system. So you can establish now secure communication.
Mm-hmm. Yeah. And when we did the encryption episode, we did, like, by hand, we did one of the, like, setting up the secure encryption, where it's like, okay, I'm going to do a math problem, and you do a math problem in secret, and then we compare the answers. We're like, yeah, but it's the same answer. Cool. Like, that's the, like, establishing the secure connection.
Yeah, but like in classical computing, right? I guess if someone was, tapped into our phone line, or whatever, the internet line, they would be able to, like, potentially see all the bits that we're sending back and forth and pick up what we're doing. And in quantum computing, we would know that they were doing that.
Right. Yeah.
Which is pretty neat. Mm-hmm. But then, I don't know much about this. I only know about this one statement, which is that so you can't clone a state, but you can teleport a state. And basically, like, those sound like kind of the same thing. Mm-hmm. The rule for teleporting a state is you can teleport a state if you destroy the state at your location. Mm-hmm. So that's kind of the one, like, trick around the no cloning theorem, I guess, is if you destroy the state, you can send it somewhere else.
Yeah. That's the Star Trek teleporter, which I think there's a CGP Grey video about it, where it's like, what happens to the original person in the teleporters? they die. Like, you have to destroy them.
They just get murdered.
Yeah. So, like, is there like this bank of dead people that went in the teleporter somewhere else that they're not showing us?
It dissolves into like or there's a trapdoor that everyone actually gets sent out.
That's I don't, never mind. I don't want to spoil a very good movie that's somewhat related to this. So, okay, I have a question for you, and it seems like people get tripped up on this, and when they announce things about the Nobel Prize winners, it makes sense to say, for experiments, doing something, pioneering something else. Not confusing, just these guys did some cool stuff, fantastic. The underlying philosophical implications from Bell, which led to these experiments, which also then led to the Nobel Prize. Bell saying, essentially, the universe is not locally real. Do you know what that means? Could you explain that? Pop quiz.
Oh gosh.
I can take a stab at it. I'm looking at something. I've just seen a lot of people ask that on the internet. Like they read about the Nobel Prize and like, that's cool. And they dig a little deeper and they're like, what the hell does that mean? Like the Nobel Prize is very practical. Like they did experiments and pioneered some cool stuff. And then like, what does it mean? It gets a little bit wonky.
Yeah, I mean, I feel like no one knows exactly what it means, but basically, I went to a talk about from this guy at San Jose State, Ken Wharton, and he'd actually be a really good person to have on the podcast as a guest.
Cool.
But he does not like the Copenhagen interpretation of quantum, and so he tries to come up with other ideas.
It seems to be the running like acceptance. Like people are like, yeah, it works, but I'm pretty sure that's not how things are actually working. There's something else going on under the hood.
Yeah. Either you care about it and you think that there's something else happening, or you just don't care. You just are happy to do the math. I think are the two like standard positions. And he in his talk was kind of saying that basically Bell's theorem says that there's like you have to break one of these three things in order for like if there is some underlying thing, you have to break one of these three things is the way he put it, and it is locality. I think is that the first one.
Yeah,
you have to break either locality, single universe, or causality. Like one of those three things has to be not correct, like in order for us to violate Bell's theorem.
Okay. I'm with you on the first two, and the third one I kind of think of as part of the first one, but maybe I'm wrong.
It's the causality thing is his particular
his spin on it. Hey-o.
Yeah. It's interesting. Yeah. But we don't have to dive deep into it here. But basically, it's kind of like what I was saying earlier. It the way I think about it, at least, is like a priori, or is there like does God or some other like all-knowing being know what the spin state is or the polarization of these photons
ahead of time?
When they were created.
Yeah. That's the like, there's some DNA inscribed fundamental property of these things that's always been determined to be the answer to the question of like, what is the spin?
Yeah.
Or polarization.
Yeah. And that must be not true. Like it must not locally be that there is, I think you put it as a stamp. I like the stamp. There's no stamp on the particle.
Yeah. Right. Ahead of time. Like there's not like this determined value that you know the answer is going to be this. And, you know, in the Bell's theorem episode, we got to the point where we're talking about gloves. And that's where we got into the superposition of like gloves behave classically. Like if you open a box and see a left-handed glove and the other box was sent, you know, light years away, you know that box has the right-handed glove because the physics of gloves is classical and those values have been true the entire time. The entire transit of the boxes of gloves being separated that far. So classically, it's cool. That's fine. There is a stamp or there is like a handedness of the glove forever on the trip to the faraway place. And you know exactly what the other box is instantly when you open your box. The problem is quantum mechanics, things that behave quantum mechanically don't have that value according to quantum mechanics on the whole trip out to the light years away. They live in a superposition of possible results, and we don't get an answer for which value is your spin until you measure it, which happens, you know, at the end of the journey. And so there's no stamp of the answer is going to be this for this particle. The answer is, according to quantum mechanics, a probability of this or that.
Right.
And the local part is the like, fine, a left-handed glove instantly tells you that there's a right-handed glove on the other side of the universe. That's not affecting the result of what the measurement is. It's always been that value. But we would expect if the quantum particles are, you know, left-handed, quantum particles, the right-handed quantum particle on the other side of the universe had to know that the result of the measurement that happened instantly ended up being this one, because before that, it was a 50-50 chance of left and right. And then all of a sudden, somebody measures left, the other one instantly has to be right. But there's no way for them to tell each other what the result of the measurement was. And so that's where the like locality comes in. It's like, how do they talk to each other? They can't communicate across the universe at that instant, hey, I'm left-handed particle.
Yeah.
You can't tell the other one that you're right-handed that quickly. That's the local restriction, is that we understand in physics that you can't communicate faster than light. So Bell's theorem, part of it is the local aspect of it. It's like, does special relativity still hold? And then the real part, so locally real, those two things combined. The real part is what we're saying with like the stamp or the DNA or the handedness being true ahead of time. There's a reality underneath the measurement where it's like, this is going to be the answer to the question we ask. And it's been that way from the beginning. Quantum mechanics implicitly has the superposition of possible answers, but it doesn't tell you which answer you're going to get when you ask the question until you actually ask it. So that's the real part. So yeah, the Bell's theorem stuff is talking about local reality, and it's saying both local and reality can't be true. Either there's faster than light communication where the measurement instantly tells the other one what to be in its measurement across the universe, or there's no reality. There's no fundamental answer to the measurement ahead of time.
Yeah. Yeah. And so people are usually happier to say, okay, well, things don't travel faster than light. So there is no like known reality ahead of time.
Yeah. We're pretty comfortable with the locality holding, but reality not holding. But it's weird because you're like, well, then what the hell happened? How did it do that? So yeah, that's where it's just like, what's happening here? And then Bell set up the experiment to test it and prove it. And these guys did that over and over again. And in doing so, set up, as you're talking about entangled states, what does it mean practically? We get some cool information applications.
Yeah. And I mean, we mentioned Closure, I think, and we mentioned Zellinger, but in between them was Aspect, maybe is how you say it. He's French. So
Aspect,
forgive me.
I don't know. It looks like aspect to me, but yes, French.
Yeah. Yeah. Forgive me for my ruining your language. So the thing that he added, I think is a little interesting. It's worth kind of talking about is he basically he was the one that proved that, like, made the experiment so that there was no faster than light travel possible, basically. So like Closure and his companions, they did this experiment by shining I think it was a mercury arc lamp or something at a piece of material that then created pairs of photons. And they would send the photons in two directions, and they would make a measurement on the polarization of each of those photons. And when the photons were created, they were sent off at 180 degrees from each other, and they get detected by these detectors that were like 5 meters apart. And apparently they were like close enough. Their experiment, there was this loophole, is what they called it, where like they were close enough in distance. And I guess it's not just that, but there's also part of this experiment is you have to actually, there's 4 possible measurements that are made in this experiment, in the CH-SH inequality. So like each person, Bob and Alice, are making 2 different angular measurements, but they pick randomly between the 2 for a total of 4 measurements. And there was some loophole that basically said, like, well, okay, these things are close enough together, and the way that they ran it is they could only set it up to make 2 of those measurements at a time. So they'd make 2 of the measurements for a while, and then they would switch it and make some random other set of 2 measurements, and then they'd switch it and make another random 2 set of measurements. But they could only do 2 at the same time. So there was this thought that somehow like the information is able to travel between the two in that period of time because they're not like switching them. Mm-hmm. And so what Aspect did is he actually made it so once the photons were created and they're on their way to the detectors, he developed a method using acousto-optic modulators to pick a direction to send the photons at random, and then that direction would measure it, pick one of the two measurements that each person was making randomly. So he could do all four measurements so he could randomly pick what was going to be measured while the photon was in transit. Mm-hmm. So that kind of closed this loophole that somehow the information could be sent back to the other device, like that the two photons could communicate.
Yeah,
basically.
The detector could be somehow biased towards this result because of the ability to communicate with the source, possibly.
Yeah. So, but now he's decoupled them because like once the photon's created, it's random after that, mm-hmm. which way the measurement is going to be made. So like the world doesn't
conspire. So we talked about in the Bell's theorem episode about the randomness coming from, at one point it was from like key clicks in like a video game. I don't know which video game, but like the random key clicking of people around the world determined the detector directions in the measurement. And then that wasn't enough. So then another one we talked about was the direction is set by the frequency of starlight from a star that's like, hundreds of millions of light years away or something like that. I don't know how far away it is, but very far in the sense that the starlight frequency, it left the star, however many hundreds of years ago or millions of years ago. So it had to have been established if there's some correlation between the direction and the direction of the detector and the direction of the particle that's being measured. That is determined that long ago. Whenever the starlight left the star, there was that connection. So
I love that. That's so smart.
Yeah.
That's so great.
In our other episode, we talked about those two random sources to set the detector directions. They're trying to close those loopholes you're talking about. So there's no possible way to get some sort of false correlation.
Yeah.
Everything you're measuring is just the fundamentals of the particles, quantum mechanics determining them or not. But it seems like it is.
Yeah. So Aspect was the first one, I guess, to do.
Okay.
To start to close the loopholes.
Cool. Yeah. Yeah. And one of these guys, I don't remember which one. I want to say Zeilinger, but it could be wrong. They've, we talk about photons, but they're like, how big can we get this stuff? Like where is quantum mechanics dictating our lives? Like if we did this experiment with people, probably not. But I think they started doing it with molecules like buckyballs, which has, a lot of carbon atoms. So not just individual particles, and they can get the same sorts of measurements and Bell inequalities from these larger systems, which are much more complicated, but they're still fundamentally quantum. And they're like, we do it with living things. And they've done it with, what are those weird little creatures that are survivable?
Tardigrades.
Yeah, tardigrades. I think they've done this experiment with tardigrades, and they've shown that they behave quantum mechanically. Bell's inequality, or the Bell's theorem holds that the inequality is violated, and those behave quantum mechanically still. So
that's wild. Yeah. Like you just freeze a tardigrade.
Yeah, you get it cold enough that quantum effects are underpinning its happenings. I don't know if it's this measurement. Maybe it's a double slit type experiment. I forget the exact details, but one of them is getting into that kind of stuff, or like how far can we push this experimentally and still see quantum effects. So these guys are just doing the fundamental quantum experiments just to push the limits of testing quantum mechanics.
That's awesome.
It's bearing on our lives. Yeah. So once we can freeze a human, I guess, and survive a double slit experiment, maybe we could have it happen.
One thing that's interesting is I heard this from Ken Morton, is apparently Clouser, he did his work at Berkeley, and there's kind of a social part of doing quantum foundation work in that other physicists don't like it.
Oh, yeah. Yeah.
because just like it's I think a lot of people feel like it's along the lines of kind of crackpot type.
Yeah, it gets there,
ideas.
like in the woo stuff.
Yeah, and but Clouser did this work at Berkeley for I think a postdoc, or maybe it was his PhD. I'm not 100%. Showed that you can violate Bell's inequality, and apparently couldn't get a job in academia after that. Like once he goes on to win a Nobel Prize for it. They didn't know that at the time, but they just thought like, this is, why are you even looking into this? This isn't like real physics.
I think I shared a story of my time at Santa Cruz. One of the professors there, long retired, but was still teaching like a course on this kind of stuff just because he enjoyed it. He said one of them, I'm guessing was Clouser, tried to or applied for a professorship at Santa Cruz and didn't get it because of what you're saying exactly. So
it must have been him. Yeah, apparently it was hard for him.
Right. Yeah. This fundamental issue. They're like, well, we're kind of fine. I don't think we need to look into it. but yeah, then you get a Nobel Prize for it. I think it's fantastic. I appreciate it for people still asking the tough questions. And we talked about, so in the Bell's theorem episode, we call it Bell's theorem, but we did talk about EPR a lot, the Einstein, Podolsky, and Rosen paper that kind of started all this in 1935, asking the question. And something we highlighted in that episode was how Einstein never felt he got his concerns recognized or voiced properly. And him and Bohr went back and forth a lot, trying to answer the fundamental questions that they were trying to get at. And Einstein still felt like he never had it resolved. And I think Bell picked up that part of it and took it to its, I think, best conclusion, where he came up with an experiment to test the thing that Einstein wasn't comfortable with. And then these guys did the experiment. So
Ken Wharton had a point that I think was interesting in his talk. And that was that it's kind of interesting, and I think so too, that most people landed on the side of Bohr in that debate between Bohr and Einstein. In that, Einstein says so the way Ken put it, I don't think it's a perfect analogy, but it's decent, was to say that okay, you see a magician and they pull a rabbit out of their hat, right? And you have two conclusions that you can draw. You can go, oh, well, he really magically pulled a rabbit out of that hat is one conclusion. Or two is oh, he did some sleight of hand. There was a, rabbit hidden somewhere and he pulled it out. And basically to equate that to the EPR paper is Einstein is the one who's saying oh no, he had a rabbit hidden up his sleeve, or there's a trap door or something. And every other physicist was no, it's really magic.
Yeah, it really happened.
Yeah. And it makes a lot of sense when you think about it. I think Einstein was definitely the logical, the rational person, just to be well, yeah, there's probably something that we don't know happening.
Right.
Why would you think that there isn't?
Yeah.
But somehow history just decided, no, yeah, it's kind of this mystical thing that we don't understand, and that's fine.
Right.
But, it turns out that they were right in the end.
Right. Yeah. And then, so we get the lineage from Einstein to the Nobel Prize in 2022. As you're saying, the experimenters get the prize. Higgs got the prize though, didn't he? But I guess it was followed up. That was after the experiment happened, but I guess that's fair. You got to wait to see if it's true.
Yeah. I don't know when they decide to give it to theorists versus experimentalists and how that whole thing works. But
I'll be honest, I don't have a good running memory of Nobel Prize winners recently. I remember the blue LED in 2012 for some reason.
Yeah, huh?
But between then and now, it's Higgs, and then I don't know what the other ones are, unfortunately. It's the thing that I don't pay attention to that closely, I think. But then this year, I was oh, nice. I know those names and I know what they did. That's cool.
Yeah. So, well, congratulations to the three of them. And we can say that they must be alive because they won a Nobel Prize.
Yep. Bell, unfortunately, did not live to see, but I'm sure, that would be interesting. I don't know which one of the three would have not gotten the award if Bell was alive. to receive it. But yeah, I mean, and we talked about in the last episode with David Merman saying a quote, or I think he was quoting somebody else saying experiments that don't get run don't have results you can talk about. So
yeah,
we can do that with the Nobel Prize going to Bell.
Cool. Well, it was nice to get back into doing some recording, and
yeah, hope to do more soon. As Zach said, yeah, just personal life has changed a lot in the last couple of years. I have a new son who's now 5 months old, and yeah, doing great. So that's
congratulations.
Thanks. That's very much a big part of my hours in the day. And then I also started a podcast hosting company, which this podcast is on currently. And so a lot of work going into that startup. So fun times. But yeah, definitely hope to get some more recording done. And I hope we get a schedule down where we can do stuff more regularly.
I'm excited to get back into it. And I feel like one thing that's different now is my brain is fully like engaged with physics all the time now. So
yeah, you're in grad school, so you're like living physics, whereas I like don't touch it at all, really at all. If I read a book at all, it's just like fiction, World War Z, getting through that book, stuff like that. So not physics stuff. Actually, that's not true. I did pick up a textbook on my iPad the other day, but it wasn't super focused because a little one crying next to me. So I didn't get a lot into it.
Difficult.
I tried reading the textbook out loud to him, and he was not happy about it. So.
Not interesting enough. Not enough pictures, Dad.
Nope. Yeah. All right, cool. Well, thanks for listening, everyone. And check us out at thehyperfine.com. And you can see all our earlier episodes and subscribe in your favorite podcast app from there.
Yeah, you can find us anywhere. You can reach me on Twitter at Physzacs, which is Phys... PHYZACS.
Nice. I'm like Tortilla on most social media platforms. Derek Padilla, like Tortilla. It's funny, the Bell's theorem, we ended with this call out also, and you had just picked Physzacs. You had just decided that's your Twitter handle. So it was a new announcement at that time in 2019.
That's funny.
Yeah. Cool. All right. Thanks, everyone. See you next time.
Have a good one.